Today, I'm going to be talking about several topics, just going over the foundation of SOSA derived from MOSA principles, and then talking about different classes of electronic warfare, types of systems, and then what are the needs for those types of electronic warfare systems, how they then can be applied with new technology into a SOSA compliant product. And then we'll get some takeaway items a little bit later on. So again, what Bob laid out, and again, we're going through the 5 basic building blocks of MOSA, which is the Modular Open System Architecture initiative defined by DoD: competition, new technology refresh, innovation, cost savings, and interoperability. Now, what happened was each of the 3 services took it upon themselves to implement their own version of MOSA. And these are kind of shown here as being derived in the 3 branches of the services: the Navy, the Army, and the Air Force, who created HOST, CMOSS, and OMS as their view of MOSA. And many of those standards that were adopted by those 3 services were all the same, especially the OpenVPX. And so it was determined that because they were so similar, that they should be unified into a single SOSA initiative, where all of those come together now under that new organization called SOSA, Sensor Open System Architecture. A nice milestone was last September when the first SOSA technical standard, release 1.0, was completed. It was a multi-year effort. It took a lot of work by a lot of engineers and government personnel dedicated to this program. It's available now for worldwide distribution, and we're already seeing a lot of foreign interest in this standard for use around the world. It's not restricted, and it can be adopted by anyone who wishes to do so. Going forward, what we'll see is that DoD procurement requirements will be mandating the open system content in the products. So that's definitely underway now. It's already started. So the 3 different classes of electronic warfare system are the electronic attack, which includes the active countermeasures, jamming, spoofing, and then the second class is electronic protection, which tends to counter the electronic attack part of electronic warfare: adaptive spectrum, spread spectrum for lower detectability, multi-static systems for redundancy. And then the third is electronic support, which is receiving signals to decide what they are and to perhaps take action to determine some strategies going forward based on what's been detected. The interesting thing is that all of these different classes of warfare systems are now able to benefit from artificial intelligence and machine learning technologies, which are becoming more and more important to electronic warfare. The artificial intelligence gives you adaptive radar countermeasures, autonomous cognitive radios, and classification of signals, identification of signals and targets, and the exploitation of the spectrum. Another part of requirements for electronic warfare is low latency. This is especially important for the countermeasures, real-time countermeasures, like airborne countermeasures for radar. Another trend is increased signal bandwidth, and then also higher signal frequencies. The carrier frequencies themselves are way, way up. And so these are some of the requirements of electronic warfare, but there are additional requirements as well. We're looking to get a higher dynamic range. What this will do is will extend the usability of gathering the information from a radar system to longer distances or getting more detail about the target. Signals are becoming more and more complex in radar to achieve some of the functions that they need to. And so as a result, the signals being acquired have to have more capabilities to decrypt and decode those signals. SWAP, of course, is extremely important, especially for airborne and the smaller UAVs that are becoming increasingly popular. And last, electronically steered phased array antennas are really becoming widely used to have multiple elements within an antenna capable of steering the receive and transmit signal beams for a lot of really nice advantages without the mechanical structures of a dish that were previously done for that kind of steering. There's some nice new technologies that are out there. The one that's really interesting, we found extreme interest in, is the RF SOC. There's a new generation 3, and this shows you the basic building blocks that are part of that chip and why it's so important. 8 channels of high-speed RF input and output with data converters running from 5 gigasamples per second for the A to Ds and 9.8 gigasamples per second for the D to As. A powerful ultra-scale plus FPGA fabric and resources, dual 100 gigabit Ethernet interface, high-speed interface engines for other I/O, PCI Express Gen 3, for example, and then a built-in farm of ARM processors to handle the system control. What you have on this single chip then is a complete 8-channel low-latency RF transceiver subsystem. And it's really ideally suited for phased array antennas because it has 8 channels of receive and transmit all built in as part of the chip itself. We're taking a look at another new device is the Xilinx ACAP Versal AI Core device. And it has a wealth of different types of processors. Over on the left top, you'll see the ARM dual-core Cortex-A72 and the Cortex-R5 processors. In the center, you'll see the UltraScale Plus programmable logic with RAM resources. Over on the right, you'll see AI engines and DSP engines. They're all joined together by a network on chip, which means communication between and among these different resources is made very efficient. There's also a platform management controller down at the lower left, and then the network at chip also connects to a lot of different interfaces to get to memory and to get off the board with very high rate multi-rate Ethernet. So it's a very, very powerful chip. And again, those structures support the artificial intelligence and machine learning that is becoming more and more important for electronic warfare. SOSA specifies a lot of VITA standards, and here are just a listing of them. There's card specs, there's mechanical power management, different I/O protocol, notably the VITA 49, which is a radio transport protocol for specifying packetization of signals, system management, VITA 46.11. There's also new connections for the backplane. Now, the rear panel I/O is mandated by SOSA for all of the analog inputs and optical inputs and outputs. And so there are new connectors that have been devised, new housings that have all been incorporated within VITA standards to support, in this example, up to 20 RF coaxial connections on the backplane and 2 optical MT ferrules, each with 24 fibers in. This gives you a lot of very high density, high performance, high bandwidth I/O across the backplane to comply with the new SOSA requirements. So here are 4 different products from Mercury that exemplify some of this technology that we've talked about in actual products that are available today. The first one on the left is a dual ACAP Versal AI Core Xilinx device that we talked about before, again with AI, ML, and DSP capabilities. This is a 6U board and a 1-inch pitch. The next one to the right is a Xeon scalable server class processor that has built-in secure embedded framework. This gives you very high security built into the hardware and the software for resistance to cybercrime, tampering, attacks, and so forth. The next one over, this is the first safe Intel Core Gen 11 processor, and this is built along a built safe, which is a very high security for aircraft as far as of mission critical support functions for flight safety. And these include the DO 254, the DO 178C standards, and again, it's very safe, highly certified processor board. The last one on the right is the RF SOC Gen 3, which has the data converters we talked about, multi-channel synchronization, the ARM processors. Again, this is a 3U VPX. So we have both 3U and 6U, a lot of choices, and these can all be used together or independently with other Mercury products or other vendor products to comply with the open standard, open vendor approach to SOSA. So what does SOSA really mean for electronic warfare? Here's some quick benefits. First of all, it's faster, easier acquisition, easier to put new technology in. It improves life cycles. It stimulates innovation. There's a competitive advantage for a vendor that does a better job of the task with better specs. And smaller vendors can compete very nicely by offering solutions to the tier one vendors, so the primes can get their systems into a bid with a high SOSA content. That'll help them win the bid and get deliveries with lower risk. We have a supply chain problem right now. We're getting through it. SOSA product breadth is going to ramp up as we get into the certification process, which is now just beginning. It's underway. Some of the takeaways here today would be there's a lot of membership, not only including DoD, but also private industry vendor organizations. We've got the technical standard released. We've got dozens of SOSA-aligned products headed for certification. DoD really is committed to SOSA, to the benefits of open standards. And even though there may be some short-term challenges like the certification process and supply chain issues, that will get better over time. And SOSA really offers a long-term, clear benefit to everybody involved in EW. Here are some links to more resources from Mercury, Pentec, SOSA websites, and the link to the SOSA technical standard. And if you'd like to join either group, you can click on these links and request membership in either one of these organizations. They're very, very valuable, both the open group and VITA. So that will do it for me. I really appreciate your attending today.